There are three technologies that can provide frustration for our scanning efforts: firewalls, network address translation, and intrusion detection systems. All three of these are pervasive in today's environment, and you can't swing a Cat5 cable before you run into at least one of them. We'll discuss each and how they can affect your results. Let's start our discussion with firewalls. A firewall is a network security system that controls network traffic passing between two networks based on a configured rule set. It establishes a barrier between a trusted, secure internal network and another network, for example, the internet, that is assumed to be insecure and untrusted. The firewall looks at packets traveling from one network to the other and either allows or denies the forwarding of the packet based on the contents of the packet headers, or sometimes the packet payload. Decisions are primarily made based on the socket, which is the source IP address and port number, and the destination IP address and port. Other values from the header can also be used to make decisions, most notably the flags from the TCP header. There are three primary types of firewalls: stateless packet filters, stateful packet filters, and application or proxy firewalls. We'll discuss each of these architectures and how they react to port scanning. Of course, we only need to discuss how firewalls handle packets directed to open ports, because closed ports are closed, right? It doesn't matter what we send to a closed port, it's going to get dropped. Before we go any further, let's discuss connect and half-open scanning now. Since both of these scan types utilize standard TCP packet streams, all firewall types react according to their rule sets. That is, if a target port is allowed by the firewall rules, the traffic is passed through. There's nothing unusual with these scan types. We'll discuss the other scan types and how they are handled by the three firewall types in the subsequent discussion. A stateless firewall is one that looks at the socket defined in every inbound packet and compares it to a list of allow and deny rules. Based on the socket and the rules, the firewall either rejects or forwards the packet onto its destination. The architecture is like that of a filtering router in that the same packet headers that flow in one side flow out the other. Packets are filtered based on information in the packet itself and have no record of prior transactions. A typical rule set might define that any inbound packets to port 80 on IP address 10.23.156.8 should be allowed, and any outbound packets from port 80 on that same IP address should also be allowed. Other rules might deny traffic on port 3306 or several other ports. Okay, let's talk about how a stateless firewall reacts to NFX and ACK port scanning. Rules are generally written to filter by port, and stateless firewalls don't inspect the TCP flags, so if our target port is open, these probes will pass through and will receive a reply in return. This should be the case for all of these scan types. As we mentioned earlier, the ACK scan will return a reset from either an open or closed port, making the results for the target system ambiguous. However, scanning ports blocked by the firewall will result in no response, since the packets will be dropped. These two sets of results allow us to determine which ports are open through the firewall and which ones are closed, thus mapping the rules. Stateful firewalls look at inbound packets and base their pass-drop decisions on either their state table or on rules that describe the allowed flags in the TCP header. Rule sets for stateful firewalls typically define allowed connections based on the TCP SYN flag that starts the three-way connection. If a rule exists that allows the establishment of a connection over the targeted port, an entry is placed in the state table, indicating an approved connection. The state table is basically a list of approved and established sockets. Subsequent packets that arrive using the same socket are passed through the firewall based on the contents of the state table alone. The advantage of a stateful firewall is that looking up sockets is far faster than looking through the rule set. Let's look at what happens when a stateful firewall is subject to an NFX scan. Recall that all these flag combinations are essentially illegal since they don't have at least one of the SYN, ACK, or reset bits set, and the RFCs state that they should be dropped. A stateful firewall should inspect the flags and drop the packet accordingly. Furthermore, since the packet doesn't have a SYN flag set and the conversation isn't in the state table, the packet should also be dropped. Recall that an ACK scan sends probes as if they were coming from the middle of a conversation with no preceding three-way handshake. In this case, the firewall is going to see the packet with the ACK flag and attempt to look up the socket in the state table, which it won't find, so the firewall should drop the packet. Application firewalls are different from both a stateless and stateful firewall in that they don't just route packets from one network to another. An application or proxy firewall presents a separate TCP/IP stack on either side of the device. Packets flowing into the device on one interface are completely unpacked down to the application layer data. The contents, if there are any, are interpreted as according to the protocol of the target application and then moved over to the other interface, where the firewall then builds a completely new set of headers on the outbound interface before sending it out. Application firewalls are specific or must have a specific module for each application protocol they wish to support. If they don't have an appropriate module to interpret the application data, they typically fall back to performing as a stateful inspection firewall. So how will an application firewall react to NFX scans? Since the packets on either side of the firewall are completely independent, any shenanigans we try and pull with invalid flags on the outside of the firewall are not going to be sent to the target. The firewall will see them and most likely drop them. Even if they are forwarded, which is unlikely, the firewall will use valid header data when building the packet on the far side of the firewall. In a similar manner, ACK scans will arrive at the firewall, and since they're not part of any valid established connection, the firewall will drop the packet. In the unlikely event that a reset is returned, it will be from the firewall and not from the target system. No matter the architecture, most firewalls have a default deny policy, meaning that at the bottom of the list of rules is a catch-all that says, if you get here, drop the packet. Another thing to be aware of is that many firewalls implement limits on packet rates. For example, when performing UDP port scanning, the target system may generate thousands of ICMP port unreachable messages. Many firewalls limit such responses to a small number per second. This type of response profile can seriously impact the speed at which a scan will complete. Detecting when you're up against a firewall isn't always easy or even possible. Some clues that can help you deduce that you've encountered a firewall are available using the previously mentioned traceroute and -O options. Another option that isn't always effective but can help is the --bad sum option, which is called like this. This option causes Nmap to create a bad checksum in the TCP header. All host IP stacks should drop these packets so that any responses, if there are any, are very likely coming from a firewall that didn't bother to verify the checksum. There are two other ways we might be able to evade firewalls. One is to use the fragmentation fields in the IP header. The physical layer imposes a restriction on the maximum size of a packet or transmission unit that can pass across it. For example, it might be 1,000 bytes. The IP layer is responsible for splitting a data stream, which may be megabytes of data, into appropriate chunks for transmission over the network. When a datagram is subject to fragmentation, the ID field in the IP header identifies the fragment with a unique identifier or number. The more fragments flag is turned on, and the fragment offset field is set to indicate the relative position of the data chunk within the overall datagram. Fragmentation helps evade firewalls because performing defragmentation is a performance hit, so firewalls will often pass the fragments uninspected through to the target. Fragmentation is most effective when we choose a fragment size that splits the TCP header into different packets. The Nmap options that enable and control fragmentation are the -F option, which requests a fragment size of 8 bytes. Using the -F option twice requests 16-byte fragments. And lastly, there's the --MTU, or maximum transmission unit option, where the user defines the size of the fragments. Here's a couple of examples using these options. Note that fragments must be specified in multiples of 8 bytes, and since the TCP header is only 20 bytes long, a single -F is the preferred and most useful option. Here's a set of headers for a typical TCP/IP packet. Using a single -F option, the header would be split into 3 sections, like this. The first packet to be sent would include the first fragment. The ID field in the IP header is set to 23087, which uniquely identifies the datagram and will be the same for all 3 fragments. The more fragments flag is set to on, and the fragment offset field is set to 0 since this is the first fragment of the series. Note that the first 8 bytes of the TCP header are included with the packet. The second packet to be sent will look like this. The ID field is the same as in the first packet. The more fragments flag is set since this isn't the last packet, and the packet offset field is set to 8, indicating that the data portion of this packet starts with the 8th byte of data from the datagram. Now the fragment data contains the second 2 lines of information from the TCP header. The last packet sent will look like this. Again, the ID field is constant. This time the more fragments flag is set to off, which tells the recipient that this is the last fragment in the series, and the offset field is set to 16, indicating that the data in the packet starts at byte 16 in the original datagram. The data contains the remainder of the TCP header. When attempting to use fragmentation, there are 2 potential issues that you need to be aware of. First, not all systems allow sourcing highly fragmented packets, and they will defragment the outgoing packets before sending them out. The Linux IP tables connection tracking module is one such system. If this is a problem on your Nmap testing system, one way to try and bypass source defragmentation is by forcing Nmap to use raw Ethernet frames. The other issue is that some firewalls queue incoming fragments and perform reassembly before forwarding them on to their destination. This, of course, defeats our reasons for using fragmentation, but isn't something that is easily detected or avoided. The other means of trying to evade a firewall is referred to as an idle scan. This scan uses the fact that some systems use a monotonically increasing ID field for each datagram sent out from that host. If we can find an idle system that isn't using or incrementing the ID field, and that system uniformly increments subsequent ID values, we can use that system to perform a scan that completely hides our identity. Very sneaky indeed. Here's the way this scan works. Suppose we've identified a printer as being idle and having monotonically increasing IP ID values. We start by sending a packet to the idle system, which sends us a reply that includes the ID value which we note. We then spoof a SYN packet to the target system using the idle system's IP address. Since the port is open, this packet elicits a SYN ACK response from the target to the idle system, which, having no knowledge of the conversation, responds back to the target with a reset packet, which burns an ID number. We then send a second packet to the idle system, which again responds with a packet and another ID value. At this point, we've received 2 ID values from the idle system. If they differ by 2, as they do in this case, we can deduce that the idle system and the target exchanged packets, and that the queried port is open on the target system from the perspective of the idle system. What if the queried port is closed? We start with the same query to the idle system and note the ID value in the response. Again, we spoof a packet to the target using the idle system's IP address. The target still responds to our spoof by sending a packet to the idle system, but this time, since the port is closed, the target sends a reset packet. The reset packet doesn't warrant a response from the idle system. We then query the idle system again and note the ID. Since the ID has only increased by 1, we can deduce that the idle system didn't respond to the target's packet and therefore conclude that the port is closed. Idle scans are sneaky and actually map the ports on the target from the perspective of the zombie, and can therefore be used to map out trust relationships. For example, we might be able to map a network administrator's access to or through the firewall if we can find a time when their system is idle. The key to using this type of scan is finding an idle system. We'll talk more about that in the module on scripts, specifically the IP-ID SEQ script. An idle scan is enabled like this, where 192.168.5.4 is the idle system, and 192.168.23.88 is our target. Okay, enough about firewall evasion. Let's talk about other things that can frustrate our scanning. Let's talk about network address translation. Network address translation is a mechanism that remaps a multitude of internal addresses onto one single public IP address. Firewalls are often configured to perform network address translation to hide the IP addressing scheme on the internal network from the outside world. Furthermore, most organizations use private RFC 1918 addresses on the internal network and have a very small set of routable addresses on the outside of the firewall and the DMZ. When scanning from an internal workstation to an outside system, there is little to worry about since appropriate address translation happens transparently. However, if the situation is reversed, we find that scanning from an external network to an internal network with a NAT enabled is very restrictive. The only IP address we can see from the external side of the NATing device is the one configured on its external interface. We have no way to define that we want to pass through the firewall to a device on the internal network. So in this case, trying to scan 172.19.5.232 from outside the firewall will not work. Finally, let's discuss intrusion detection systems. A network intrusion detection system, or IDS, is a device that monitors network traffic for malicious activity and produces reports about policy violations, which are published to a management station. Network intrusion detection systems are placed at strategic points within the network to monitor traffic to and from all devices on the network. It works in promiscuous mode and performs analysis of passing traffic for the entire subnet. Once an attack is identified or abnormal behavior is sensed, an alert can be sent to a network administrator. An IDS can be configured to look for many signs of attack, including signatures, header anomalies, and packet rates. One way to avoid triggering an alert on an IDS due to an excessively high packet rate is to set a performance template sufficiently low to avoid detection. How low might need to be determined by testing using several expendable IP addresses. Other ways include making your traffic look as legitimate as possible. Two options that allow you to do that are the --source-port number and the --data-length option, which appends random data to a sent packet. These options could be used together in a host enumeration scan to make your traffic look like it was coming from a secure web server with an encrypted payload. We can also hide ourselves as the source of the probes. The -S option can be used to spoof a source IP address that isn't really ours. This can create some interesting traffic on the target, but since any replies will be routed to the spoofed address, it isn't really useful from an information gathering point of view unless we're performing an idle scan. There are legitimate uses for this option. For instance, we might have multiple addresses associated with one network card, or we might even have multiple network cards, in which case the -E option will be useful as well. Similarly, we can set a fictitious MAC address in the physical layer header to make it look like our card is from a different manufacturer. While this won't fool anyone for very long, it can deflect suspicion for a while. The argument to the --spoof-MAC option can be a full MAC address, a vendor's prefix, or the vendor's name. Here's a few examples. The last one sets the MAC address's first 3 bytes of data to match Cisco's prefix, and then the last 3 bytes of the MAC are by default set to random data. One last way we can hide our scans is to flood the IDS with misleading data. The -D option allows us to specify other addresses that should be used as decoys. The target host will see that it is being scanned from multiple hosts and won't know for sure which one is really initiating the probes and which ones are innocent. This example specifies that only 2 IP addresses be used as decoys, but in practice, if you really want to hide, you should list more. Use caution when using this option since Nmap has to generate a complete set of probes for every decoy, which can significantly degrade the performance and speed of your scan. In this module, we've presented some of the challenges and techniques for dealing with firewalls, intrusion detection systems, and network address translation. Modern firewalls are very good at what they do, and in the hands of a skilled administrator can prevent you from getting through. But not all admins are highly skilled, and mistakes can happen. Nmap can be used to audit a firewall and discover the holes in a configuration. In the next module, we're going to move on from port scanning and present version and OS detection.